Dear friends, today we will discuss small sample test. Let us see the introduction of small sample test. When sample size is small, that means n is less than 30, the central limit theorem does not assure to assume the distribution of sample statistics as normal. When the sample size is small, the special probability distributions are used to determine critical value for the test statistic. Here, we must have to assume that the small sample is drawn from the normal population, and based on it, some important distributions and their applications in testing of hypothesis are discussed. Let us see t distribution. If x1, x2, xn are independent observations drawn from normal population with mean mu and standard deviation sigma, then the probability distribution of statistic t equal to x bar minus mu divided by s by root n, where s square equal to summation I1 to n xi minus x bar whole square divided by n minus 1 is called students t distribution, or simply t distribution with n minus 1 degrees of freedom. Degrees of freedom indicates the number of independent terms in statistic. As the restriction on statistic increases, the degrees of freedom decreases by that much restrictions. Let us see an important properties of t distribution. Few important properties are as under. Number 1, it is a continuous distribution with range minus infinity to infinity. Number 2, probability curve of t distribution is symmetric about its mean. Number 3, its mean is always 0. Number 4, for large value of sample size, it follows normal distribution. Let us see applications of t distribution. Some important applications of t distributions are as under. Number 1, to test significance of the mean. Number 2, to test the significance of two means. Number 3, to test the effectiveness of treatment given to data values, that is pair t-test. Let us see the above applications by considering suitable illustrations. Number 1, to test the significance of the mean. This test is used to test the hypothesis that there is no significant difference between sample and population mean, or sample has been drawn from the normal population with specified mean. Let us see illustration number 1. A sample of 4 observations from a normal population gives mean 1.75 and variance 0.6875. Test the hypothesis that the population mean is 2. Let us see the solution. Step 1. Here sample size n equal to 4, sample mean x bar is 1.75, sample variance s square is 0.6875, and therefore its square root s equal to 0.8292. We have given population parameter mu equal to 2 and alpha level of significance is 0.05 and degrees of freedom equal to n minus 1. Here n is 4, so degrees of freedom becomes 3. Step 2. In this step we define our hypothesis, null hypothesis and alternative hypothesis. The null hypothesis H0 is mu equal to 2 versus alternative hypothesis H1 mu not equal to 2. Step 3. In this step we will define test statistic. In step 3, let us first find the absolute difference of x bar and mu. So, absolute difference of x bar minus mu equal to 0.25 and standard error equal to s divided by root n minus 1, which is equal to 0.8292 divided by root 3. Under H0, the test statistic is given by modulus t equal to the absolute difference divided by standard error. Substituting the answer of absolute difference and standard error, we get the value of test statistic mod z equal to 0.52. Now step 4. Since the given test is two-tailed test, hence the critical value for 5% level of significance with 3 degrees of freedom is obtained from the tables of t distribution and it is 3.183. Since 0.52 is less than 3.183, hence the null hypothesis is not rejected. Step 5. At 5% level of significance, we do not reject the null hypothesis, hence we conclude that the population mean is 2. Let us see example number 2 to test the significance of two means. This test is used to test the hypothesis that there is no significant difference between two population means or two sample has been drawn from the normal population with equal mean. Illustration 2. The following information is obtained for two samples drawn from two normal populations. In the data we have given sample 1 and 2, corresponding size 10 and 12, mean 12 and 15 and standard deviations 3.162 and 5.115. Can we say that the two population means are equal? Let us see the solution. Step 1. Here n1 equal to 10, x1 bar equal to 12, s1 equal to 3.162, n2 equal to 12, x2 bar equal to 15, s2 equal to 5.115. Step 2. Our null hypothesis H0 is mu1 equal to mu2 versus H1 mu1 not equal to mu2. Step 3. We find the difference x1 bar minus x2 bar and its modulus value. That means modulus of 12 minus 15 equal to 3. Now under H0, the test statistic is defined as absolute t equal to absolute difference x1 bar minus x2 bar divided by s into under root 1 upon n1 plus 1 upon n2, where s is under root n1 s1 square plus n2 s2 square upon n1 plus n2 minus 2. Substituting the value of n1, s1, n2, s2, we get under root 10 into 3.162 square plus 12 into 5.115 square divided by 10 plus 12 minus 2. On simplification, we get 4.5494. Hence, the value of test statistic modulus t equal to modulus 12 minus 15 divided by 4.5494 into under root 1 upon 10 plus 1 upon 12, which is equal to 3 divided by 1.9479 equal to 1.5401. Now step 4. Since the given test is two-tailed test, hence the critical value for 5% level of significance with 20 degrees of freedom is obtained from the table of t distribution and is 2.074. Since 1.5401 is less than 2.074, hence the null hypothesis is not rejected. Step 5. At 5% level of significance, we do not reject null hypothesis, hence we conclude that the population means are equal. Number 3. To test the effectiveness of treatment given to data values, that is paired t-test. This test is used to test the hypothesis that the treatment given to the observations is ineffective, that is, there is no significant difference in the value of observations before and after giving treatment. Let us see the example. Illustration 3. A data of sales of an item in 6 shops before and after special sales promotional campaigning are as under. Shops 1, 2, 3, 4, 5, 6. Before campaigning, the values are 53, 28, 32, 48, 50 and 42. After campaigning, in the same shops, the values are 58, 32, 30, 50, 56 and 45. Can the campaigning be regarded as success? Let us see the solution. Step 1. Here we calculate from the given data the difference between the campaigning before and after. In first column, we have given the different shops 1 to 6. Second column indicate the figures before campaigning. Third column indicate the figures after campaigning. The fourth column D indicate the difference between the before and after. That means 53 and 58, the difference is 5. Similarly, 28 and 32 difference is 4. Here the difference is calculated as a after campaigning minus before campaigning. So, similarly we can calculate the column difference D, and the last column we consider the square of the difference, that means D square. So, square of 5 is 25, square of 4 is 16, and so on. Now, from the given data and above table, we find sample size n equal to 6, average value of the difference d bar, which is summation d divided by n, equal to 18 divided by 6, which is equal to 3, s square equal to 1 upon n summation d square minus square of summation d divided by n. Substituting the value of summation d square and summation d from the earlier table, we can find value 1 upon 6 into 94 minus square of 18 divided by 6. On simplification, we get the value of s square 6.667. If we find the square root of this s square, we get the standard deviation s equal to 2.58. And we have given level of significance alpha 0.05 and degrees of freedom n minus 1 is 5. Now, in step 2, we define the hypothesis. Null hypothesis H0 is campaigning is ineffective versus alternative hypothesis H1 is campaigning is effective. In step 3, we calculate the value of test statistic. The absolute difference given by absolute difference of d bar, which is equal to 3, standard error equal to s divided by root n minus 1, which is equal to 2.58 divided by root 5. Under H0, the test statistic is defined as modulus t equal to modulus difference divided by standard error. Substituting the above result of modulus difference and standard error, we get the value of test statistic modulus t equal to 2.6. Now, in step 4, we take how to take the decision. Since the critical value for 5% level of significance with 5 degrees of freedom is obtained from the table of t distribution and is 2.571. Since 2.6 is greater than 2.571, the null hypothesis is rejected. Now, in step 5, we give the conclusion. At 5% level of significance, with we reject null hypothesis, and hence we conclude that the campaigning is successful. Let us see F distribution. Let us first define the definition of F distribution. If chi1 square is a chi-square variate with n1 degrees of freedom and chi2 square is another independent chi-square variate with n2 degrees of freedom, then the distribution of the ratio chi1 square upon n1 divided by chi2 square upon n2 is called F distribution with n1 and n2 degrees of freedom. To test the equality of means of two small samples, we use t distribution. In applying t distribution, it is assumed that the populations from which samples are drawn have equal variances. Hence, before applying t test, it is necessary to test equality of population variances. For that, F distribution is used. Consider the following illustration for the application of F distribution. Let us see illustration 4. The following information is obtained for two samples drawn from two normal populations. In the data, we have given sample size, sample mean and sample standard deviation for two samples. For sample 1, size is 10, mean is 12 and standard deviation 3.162. For sample 2, size is 12, mean 15 and standard deviation 5.115. Can we say that the two population variances are equal? Let us see the solution. In step 1, we have given sample size for two samples, that is n1 equal to 10 and n2 equal to 12. Similarly, the sample variance is s1 square equal to square of 3.162 which comes out 9.9982. Similarly, square of S2, which is nothing but the variance of second sample, is square of 5.115, which is equal to 26.1632, and alpha level of significance is 0.05. Degrees of freedom n2 minus 1 and n1 minus 1 becomes 11 and 9. In step 2, we define the hypothesis. Null hypothesis H0 sigma 1 square equal to sigma 2 square versus H1 sigma 1 square not equal to sigma 2 square. In step 3, we define test statistic. The test statistic is, since S2 square is greater than S1 square, it is defined as f equal to n2 into S2 square divided by n2 minus 1 whole divided by n1 into S1 square divided by n1 minus 1. Substituting the values of n1, n2, S1 square and S2 square, the f statistic becomes 2.5692. In step 4, we proceed for conclusion. Since the critical value for 5% level of significance with 11 and 9 degrees of freedom is obtained from the tables of F distribution and is 3.10. Since 2.5692 is less than 3.10, the null hypothesis is not rejected. Step 5. Let us define the conclusion. At 5% level of significance, we accept null hypothesis. Hence, we conclude that both the population variances are equal. We know that for small samples, the significance between two means can be tested by t-test, but in practice, we may like to test equality of means of several samples. In such situations, t-test is not applicable. In such situations, f-test is used to test average variations among various samples, which is known as analysis of variance is used. It is a process of determining various factors which influence the value of variance. It is a technique of dividing the total variations of the data into component variations due to various sources. The process of separating only one source of variation from total variation is called one-way analysis of variance or one-way ANOVA. And if we separate two sources of variation, then it is called two-way ANOVA. For the application of F distribution, in such cases, it is assumed that all samples have been independently drawn from the same population with same variance. Let us consider the following illustrations for the ANOVA. Illustration 5. The following information is obtained by using 3 fertilizers in different plots. Here we have given 3 fertilizers A, B and C and corresponding yield quintal per acre given in 4 plots as for fertilizer A, the values are 1, 4, 3, 3. For fertilizers B, values are 6, 5, 4, 2. And for fertilizer C, the values are 7, 3, 5 and 6. Test the hypothesis that there is no significant difference between the mean productivities due to different fertilizers. Let us see the solution. Here only one source is to be determined, so it is called one-way analysis of variance. In step 1, here we have given the values of the yield due to different fertilizers under different 4 plots. Let us find the first total yield for fertilizer A, that is the sum of 1, 4, 3, 3, which comes out 11. Similarly, for fertilizer B, the total becomes 17, and for fertilizer C, the total is 21, and total of all these totals is 49. We call it grand total. Here grand total G is equal to 49. Correction factor CF equal to G square divided by capital N. Capital N is 12. Grand total is 49. Substituting in the formula of correction factor, we get the answer 200.08. Let us calculate now total sum of squares. Total sum of square is given by double summation xij square minus cf. Double summation xij square, that means the sum of square of every value of all the plots given in the data. So 1 square plus 4 square plus 3 square till the last value 6 square minus cf is 200.08. On simplification, we get total sum of square equal to 34.92. Now we calculate sum of square due to fertilizer or row sum of squares. Row sum of square equal to summation rj square divided by k minus cf. Here rj indicate the total of the jth row. From the above table, we find the totals and substituting these values, we get 11 square plus 17 square plus 21 square divided by 4 minus correction factor 200.08. On simplification, we get row sum of squares equal to 12.67. Now last we calculate error sum of squares. So error sum of square equal to total sum of square minus row sum of square. Substituting both the values, 34.92 minus 12.67, which becomes 22.25. Now we define the hypothesis. Step 2. The null hypothesis H0. There is no significant difference in the mean productivities due to different fertilizers. In step 3, we prepare ANOVA table as follows. First column indicate the source due to fertilizers, due to error and total. Second column indicates sum of squares, which we have calculated earlier. Substituting all the three answers of the sum of square, we get the value for fertilizer 12.67, for error 22.25 and for total 34.92. In third column, we calculate degrees of freedom. For fertilizer 3 minus 1 equal to 2, for error 11 minus 2 equal to 9 and for total 12 minus 1 equal to 11. In next column, we calculate mean sum of square. Due to fertilizer equal to mean sum of square can be obtained as sum of square divided by degrees of freedom. So here we divide 12.67 by degrees of freedom 2, we get the answer 6.335. Similarly, due to error, the mean sum of square is obtained as 22.25 divided by 9, so we get the answer 2.47. Now we calculate the value of the F calculated statistic. F calculated statistic is given by mean sum of square of fertilizer divided by mean sum of square due to error. That means 6.335 divided by 2.47. We get the answer 2.56. And from the table of F distribution with 2 and 9 degrees of freedom at 5% of level, we get the tabulated value 4.26. So in step 4, we describe the decision. Since critical value for 5% level of significant with 2 and 9 degrees of freedom from the table of F distribution is 4.26. 2.56 is less than 4.26, so the null hypothesis is not rejected. Step 5. At 5% level of significance, with we do not reject the null hypothesis, hence we conclude that the variations due to fertilizers is insignificant. Let us see illustration 6. The following information is obtained for the productions of 3 operators on 4 machines. We have given 3 operators ABC and 4 machines. The corresponding production in units are given in the table. For operator A, for machine 1, production is 560, next machine 540, 580 and 560. Similarly, for production on machines for operators B and C are given in the table. Analyze the data for number 1, there is no significant difference among operators. Second, there is no significant difference among machines. Let us see the solution. Here two sources are to be determined. So, it is called two-way analysis of variance. Here we subtract 580 from each observation and then divide it by 10. Then we have the following table. In this table, operators ABC and machines values are reduced -2, -4, 0, -2 and so on. We have made a total for row wise and column wise. Totals of the 3 rows are -8, 0 and -4. Similarly, totals for columns are -3, -9, 0, 0 and grand total is -12. So, we denote grand total G by -12. Correction factor CF equal to G square upon N. Substituting the value of G -12, its square becomes 144 divided by 12, which is equal to 12. Now, we calculate different sum of squares. First, total sum of squares. Total sum of squares equal to double summation Xij square minus Cf. Here double summation Xij square means sum of square of all the values of the given table, which comes out 48 minus Cf equal to 12. So, we get the answer 36. Now, we calculate sum of squares due to operators, that means row sum of squares, which is given by RSS equal to summation Rj square divided by K minus Cf. Substituting the values of the row total -8, 0 and 4 in the formula, we get -8 square plus 0 square plus -4 square divided by 4 minus 12, which comes out 8. Now, we calculate sum of squares due to machine, that means column sum of squares. The formula for column sum of square equal to summation Cj square divided by M minus Cf. So, Cj indicate the total of jth column. Substituting the total of the every columns and find its square and total. So, we get -3 square plus -9 square plus 0 square plus 0 square divided by 3 minus correction factor 12. On simplification, we get answer 18. Now, we calculate error sum of square using the formula error sum of square equal to total sum of square minus row sum of square minus column sum of square. Substituting the values of all the 3 sum of square, that means 36 minus 8 minus 18, we get answer 10. Now, in step 2, we define hypothesis. There are 2 null hypotheses. Number 1, there is no significant difference among operators. Number 2, there is no significant difference among machines. To test this hypothesis, we prepare ANOVA table as defined in step 3. In ANOVA table, first column indicate the sources, second column indicates sum of square, third column denote degrees of freedom, fourth column denote mean sum of square, fifth column denote the calculated value of F statistic, and last column denote the tabulated value of F. Due to operators, the sum of squares we have earlier calculated, which is 8, its degrees of freedom is 2. So, mean sum of square equal to sum of square divided by degrees of freedom, which gives the value 4. Similarly, due to machines, sum of squares is 18, degrees of freedom is 3, and therefore, mean sum of square equal to 18 divided by 3, which is 6. And due to error, sum of square is 10, degrees of freedom is 6, therefore, mean sum of square is 10 divided by 6, which is 1.67. And now, we calculate the value of the test statistics, which is F calculated for operators, which is given by the value 4 divided by values of mean error sum of square 1.67, which comes out 2.4. Similarly, F calculated for machines is calculated as the ratio of 6 divided by 1.67, which comes out 3.6. Now, we see in the F table for operators degrees of freedom 2 and 6, and for machines degrees of freedom 3 and 6. Let us see in next step. In step 4, since the critical values for 5% level of significant with 2 and 6 degrees of freedom and 3 and 6 degrees of freedom are respectively obtained from the table of F distribution are 5.14 and 4.76. Now we take a decision A. 2.4 is less than 5.14, hence the null hypothesis 1 is not rejected. Similarly, B. 3.6 is less than 4.76, hence the null hypothesis in 2 is also not rejected. Step 5. At 5% level of significance, we accept null hypothesis and hence we conclude that the variations due to operators and machines are insignificant. Let us summarize the talk. We have discussed small sample test, that is sample size less than 30 based on T distribution and F distribution. The tests based on T distributions are t-test for single mean, test for two means for independent samples and pair t-test for dependent samples. The applications of F distributions are testing the equality of two variances, testing the equality of 3 or more means of independent populations, which we call ANOVA test, and for the above test we have discussed various types of examples. Thank you.